in BJT Part 2. Okay, so the topic covered, okay, so, the outline for this Part 2 is BJT as amplifier circuit for the common emitter, common base, and common collector. And then the DC analysis, Q points, same like BJT. BJT has Q points, so as the, same like diode. Diode has Q point where you did on the mathematical and as well as the graphical. Okay, same goes to the BJT. The same concept, okay, where you solve your circuit using mathematical, KVL equation, and so on. And also, the second method is by using graphical. Okay, there will be 3 configuration only, which covered in your syllabus, which are fixed bias. Okay, we have looked through this, okay, the fixed bias, and also the emitter stabilized bias and the voltage divider. You might have forgotten about the fixed bias where we have started in the last week. I will give you a short recall on the fixed bias. Okay, so we have done this. All right, so this is the circuit. So for the common emitter, so in the syllabus we'll cover only the common emitter. So for the common emitter means that emitter is grounded. So this is one example of the amplifier circuit. Okay, so a complete circuit of the BJT or amplifier must has the capacitor. So in your syllabus, you will be analyzing the DC part and also the AC part. Okay, for the DC part, okay, what happened to all this capacitor? It must be open circuit. Okay, when you open circuit all the capacitor, the remaining circuit will become like this. Okay, just like this. So this circuit, you're going to analyze it. When it means DC analyzation, means you have to find the current values and as well as the voltage values. Okay, so for example, in BJT, it has 3 terminals: base, collector, and emitter. Therefore, there are voltage and currents involved with this terminal where you have IB, IC, IE. Okay, so as the voltage where you have VB, VC, and VCE. All right, like I said, we have, for your syllabus, you're going to have 3 types of biasing configuration. Okay, the first one is fixed bias, second one emitter stabilized bias, and third one is voltage divider. So all this has different circuit connections. So you have looked through the fixed bias. Okay, so we are going to recall it a bit. So this is the important equations that you need to know. Okay, every time you solve the DC analysis circuit for BJT, so these are the important equations that you need to know. Then you have to memorize it until this week. You should have already memorized this. Okay. So for the BBE voltage, it is fixed. If it is usually it is made of silicon, therefore 0.7 volt. IC is equal to the beta IB, IE is equal to IC plus beta IB, and IE is equal to beta plus 1 IB. So how we derive this is in the previous lecture, part 1, right? So this is how it looks on the fixed bias. Okay, fixed bias means the emitter doesn't has resistor and it is straight away to the ground. Okay, so like I said, the complete circuit must be together with the capacitor. But then when you analyze the DC analysis, which is in the current part right now, so you open circuit the capacitor. All right. So these are the steps to solve it. Okay, first you remove the capacitor. Okay, you remove the capacitor and it will looks like this. Okay, without a capacitor, so you have again. So every time you got you do BJT DC analysis, so you have to put all the notation. Okay, for example, you have base, collector, and emitter. So so this is your base, collector, and emitter. So in between junction, you have voltage. Okay, so you have VBE as well as VCE. Okay, and then you have current also, which is IB at the base. Okay, and also you have current at IC at the collector. Okay, in this case, emitter is ground, therefore emitter is no current at emitter because emitter is grounded. VE is 0 for this case. Okay, so second step is you separate between input loop and output loop. Okay, so from the input loop you have base to emitter. Okay, at the output loop you have from collector to emitter. Okay, this doesn't show the same like I have shown you in the previous class, but later we'll look through it. Okay, so this is quite pretty similar from what I have drawn in the last class last time. Okay, so this is the input loop where you solve the KVL at the input loop, and this is the output loop where you solve the KVL at the output loop. So I sum up everything in this slide, okay, where you open circuit the capacitor for the first step, okay, and then the second step is the input loop, okay. So I have drawn it pretty much similar actually. So this is at the input loop. And this is at the output loop. So as you can see at the this is at the input loop. All right, so you have voltage, okay, 12 volt. Okay, this is referring to this example. Okay, so you have to separate between input and output. Okay, so the input loop, okay, which I have summarized it like this. So at the input loop you have base and emitter. From base, okay, from base here you have so this is your base. Okay, from base here you have RB. So I have drawn RB. So you have to go from node to node. Okay, now you have from base you have RB and then VCC. So that's why base you have RB and then connect to plus VCC. Where does the negative goes? Of course, every time it will go back to the ground. Okay, now your emitter is grounded. So this is grounded. Okay, so that's it for the input loop. Okay, you have to solve the KVL at the input loop. So you have minus 12 plus IBRB. Don't forget you have voltage junction here. Every time when you do BJT analysis, you have to write the voltage here. And then you get plus VBE. 0.7 and then find the IBQ. So IBQ is about this value. Okay, so from this important equation, you know that ICQ is beta IB. Okay, beta is given 50 in the question. Therefore, you can straight away calculate the IC. Okay, so for the output loop, okay, for the output loop, so output loop is from here. From collector to emitter. So this is your output loop, VCC, RC, and VCE. So when you draw again, so this is how it looks like. From collector, you have resistor RC. Resistor RC connect to plus 12 volt and then negative goes to the ground. Okay, and then you apply KVL. So this is how you get the KVL. Negative 12 plus 2.2 KIC plus VCE equal to 0. Right, so finally the objective is to find the output voltage, which is the VCE, which is equal to 12 minus 2.2 KIC. Where did you get this IC? Is from here. All right, and then the question asks you to calculate all this voltage. Okay, so all this voltage is actually from that. If VB means that from base terminal to the ground, if VC from collector terminal to the ground, if VBC means from base to collector. So how you do it? So I have teach you. I think the simplest way without seeing where is the voltage notation. So when it is VBE, therefore means VB minus VE. So from here you can get VB. If VCE means VC minus VE. So from here you can get VC. Okay, since emitter is grounded, there is no resistor here. Therefore VE is 0 volt. Right? Okay, so I ask you to do this exercise. Okay, so have you tried this exercise? Have you all tried this exercise?
Yes.
All right. So did you get the answer?
Yeah.
Okay. So how much is the answer for? Oh, I also don't have it. Yeah. Okay. Okay. So I think this is not much different, okay, from this example, except for the values of resistor. Okay, if you didn't try it, this is too bad. Okay, this is good exercise. Okay, so now tell me, what is IB? Is someone try? Okay, so what is IBQ? Can someone give me the answer for those who have tried? This circuit is exactly the same like in example, except the values of resistor and voltage. Okay, you should be able to do this.
Madam, I get 3.26 10 to the power of -5.
Thank you. 3.26 10 to power of -5 ampere. All right. So ICQ is equal to beta IB. How much?
2.93 milliampere.
All right. Great. Thank you. Only Peng Ang try. Did anyone get the same answer like Peng Ang?
Yes, Sam.
Same answer. All right. So how about VCEQ?
8.09.
All right. Great. Okay. So how about VB?
VB is 0.7.
0.7.
Okay. Oh, 7. Okay. Okay, and then VC?
VC is 8.09 also. Same with VCQ.
Correct, because emitter is 0. Okay. VE is 0 volt.
0.
All right, great. Okay, so thank you for those who tried. Okay, this is a good exercise for you to try. I hope that everyone also try and get the same answer like this. Okay. Okay, so we've done with the fixed bias. So please remember, when you have a circuit with emitter to ground, there is no emitter resistor. There is no resistor at the emitter. Therefore, the name of this circuit is fixed bias. Okay. However, since we have 3 types of biasing, okay, so you have fixed bias, emitter stabilized bias, and voltage divider bias. Of course, emitter stabilized bias is better than fixed bias, and voltage divider bias is better than fixed bias and emitter stabilized bias. So this configuration is become more and more stable. Okay. All right, so when I said this emitter stabilized bias is better than fixed bias, of course, fixed bias has disadvantages. So what are the disadvantages? So for the emitter stabilized bias, since it doesn't have resistor at the emitter here, therefore it is unstable. Unstable in terms of the beta, because this BJT circuit too depends on the beta. Okay, when the beta change, or the Q point also change, means the active values and the values at active regions do change and too depends on the beta. Okay, how do we improve the stability? Therefore, we add emitter resistor to the circuit. Okay, where do we add the resistor? Is at emitter terminal. Okay, so here you go, comes with the second type of biasing circuit, which is emitter stabilized bias. So for this emitter stabilized bias, so this is how it looks like, where now instead of fixed bias doesn't have resistor at the emitter, now at fixed bias, emitter stabilized bias, it has resistor at emitter. As you can see, if I write again the notation, so you have base, collector, and emitter. As you can see, at emitter you have resistor. Okay, therefore your KVL will be a little bit different from the previous one. Okay, so from here to here you have VE and also VCE. Okay, so in here, so emitter resistor. Why we put emitter resistor? Because we want to improve the stability level of the fixed bias configuration. Okay, again and again, I put this again and again so that you can always memorize it. Okay, so for now, we're going to use IE because now we have resistor at ammeter. Therefore, there must be a current across that ammeter resistor. Okay, resistor at the ammeter. Okay, step to solve it. Of course, first step, you open circuit the capacitor. Okay, so the circuit will turn into like this. Okay, you have base, collector, and ammeter here. Right, so you have the resistors. Okay, second step, of course, you separate between input loop and output loop. Okay, input loop is from base to ammeter. Okay, output loop from collector to ammeter. Okay, so this is how they solve it, the input loop. Okay, for the input loop, as you can see from here. So this is your input loop. So this is the KVL. Okay, KVL. Okay, if I can draw, it is the same thing. Okay, if I draw again, also the same thing. Okay, so for the KVL here, so let's write together the KVL. So KVL here will be negative VCC. Okay, and then you have IBRB plus IBRB. Okay. Okay, do not forget that the current flow at the VBE as well, plus VBE. Okay, now we also have resistor here, therefore you have plus IE RE equal to 0. All right. Okay, now you have two parameter now, IB and IE. Okay, so how you going to simplify this equation? Okay, let's take a look on the equation here. So I want to copy here. Wait. So let's copy here. So, oh, I can't see it. Does it matter? I put it here maybe. Okay, so I put the equation here. Okay, so now we want to simplify or this equation. Okay, we have IE and also IB. So what can we do? Okay, from this equation, we know that IE is equal to beta plus 1 IB. Okay, so what we do is, okay, we simplify this equation. We replace, okay, you have V minus VCC plus IBRB. And then you have VBE, okay? Okay, and then you have IE now, you replace with IB, okay, beta plus 1 RE equal to 0. Okay, that's how you simplify the circuit. Okay, now you combine the IB. Okay, finally you will get IB is equal to VCC minus VBE over RB plus beta plus 1 RE. Okay, so that's why they get this equation. Okay, same thing. You derive it or you don't derive it, you will get the same thing. All right. Okay, so that's how you do it. Okay. Okay, for example, if you want to find VB, okay, VB here, VB is actually voltage from this base, okay, to the ground. Okay, so this is VB, okay, VB. So what can you see from this base node to the ground? Okay, so you are actually seeing that you got VBE as well as voltage across RE. Okay, that's why you have here VB, okay, is equal to what you see from this node. okay, to the ground, you see you got VBE, okay, and also you got VE here, okay, VE, this is VE, okay, plus VE, okay, that's how you got the VB, okay, or you can use VBE is equal to VB minus VE, therefore VB equal to VBE plus VE, okay, so in this case, okay, VBE you already know, for example, 0.7 volt. How about VE? VE is equal to what? Here, in this case, student, from this node to the ground, what can you see? What is VE here?
REIE.
All right, correct. So it is equal to IE, RE. Okay, where can you get IE? Okay, since you already got IB here, okay, since you already got the value of IB here, therefore it is equal to IB plus beta times beta plus 1 RE. All right, so that's how you do it. Okay, so this is for the input load. Okay, for the output load, okay, so you solve KVL from collector to emitter. So this is your loop. You have resistor RC, you have VCC, and then you have RE. Okay, so write down the equation. So what is the equation here? Is KVL at this loop. Okay, KVL at this loop. Okay, so you have here, for example, or if you want to do the loop like this also can, either way can. Okay, so you have here negative VCC. Okay, look at the red loop. Okay, VCC, and then you have negative VCC, and then you have ICRC. Okay, do not forget you always have to put your VCE. This is your output voltage. Okay, plus VCE. Okay, and also the loop now you have IE, okay, plus IE RE equal to 0. Okay. So here, like in this slide, okay, looking at this equation, okay, this equation as you can see, so you can actually approximate IC is equal to the IE. All right, so that's why this one, they approximate IC equal to IE. Okay, since IC, okay, and IE are equal, okay, so you can actually make this two, since IC is equal to IE. Okay, therefore, your objective is to find VCE. Therefore, VCE is equal to the VCC minus IC times RC plus RE. So you might ask me, Doctor, can I just calculate IC is equal to beta IB because at the input loop you already have the value for IB? Okay, for example, given also beta. So can you can I calculate the IC equal to beta IB, and then IE I want to calculate IB beta plus 1? Also can, doesn't matter. You will get almost similar answer. Okay, almost similar answer. All right, so now this for this one, okay, that's why they've gotten this equation. This is the same one like I have derived it here. Okay, so for example, they ask you to find the collector VC. Okay, VC. So you have VC is this node. Okay, so from this node to the ground, that, let's say you want to find VC. So this is your VC. Okay, VC from collector node here to the ground. Okay, what you see from collector node to the ground. Okay, so you are actually seeing VC. Okay, from that node to the ground, you actually can see what? You can see you have VCE. Okay, total voltage there, VCE plus VE. Okay, as you can see from this node, okay, to the ground, okay, you can actually see VCE plus VE. Okay, that's why this equation they write VC is equal to VCE plus VE. Okay, so that's how you do it, right? Okay, to test your understanding, okay, I'll give you about 5 minutes. Okay, doesn't matter. All right. So I guess we do it together for this example too. Okay, for this example too. For the exercise, I will ask you to do on your own. Okay. After that. Okay. So let me copy first. Okay. So in this question, they ask you to find, so given this circuit, okay, and then as you can see, you have capacitor, 3 capacitor. For the DC analysis, you have to open circuit the capacitor, everything, okay? And then from here, you will have to calculate all the DC values needed, okay? IB, IC, VCE, VC, VE, VB, Z. Okay, so let's do it together. Okay, first step is open circuit the capacitor. Okay, so first step. Okay, open circuit all capacitor. Okay, when you open circuit, you redraw, you will get something like this. So you have your BJT, and then you have your resistor, another resistor here. Okay, and then you have 20 volt. Okay, this is 430 k ohm. Okay, this is 2 k ohm. Okay, and this is 1 k ohm. Right, so you open circuit all the capacitor. Okay, don't forget, this is, since you're not familiar like yet, then you have to write all the notation. So you have base, collector, emitter. Okay, from base to emitter, you have VBE, right? From collector to emitter, you have VCE. All right, so now second step is to separate the input loop and output loop. Okay, so now I want to make second step as the KVL at input loop. Okay, so let's draw at the input loop. So how it looks like, again, you have to draw the major thing first, which is your, can I write here? Okay, so second step, okay, KVL at input loop. All right, so you draw again. So you have this one, your BJT. Okay, input loop means where? From base to emitter. Okay, what you can see from base to emitter. So just base to emitter. Okay, let's start from the base. Okay, from the base here, base, okay, you have resistor 430K. Okay, write down 430K. Okay, and then 430K is connected to the plus 20 volt. Okay, plus 20 volt. Right. So where does the negative go? Of course, it will go to the ground. Okay, leave it there just like that. Okay, and then at ammeter, what do you have here? You have resistor 1K ohm. Okay, so you put your resistor 1K ohm here. Okay, where does it go? To the ground. Okay, so your negative voltage of the 20 volt also go to the ground. So you have 1K here. Okay, every time, since you're not familiar, don't forget to write your voltage junction here. Okay, so you have VBE. Okay, student might always forget to write this, and in your KVL will be wrong lah because you didn't consider the VBE. Okay, and then there you go. What else? You have IB here. Okay, of course you have IB. Okay, and also you have IE here. All right, there you go. That's it. All the notation already put. Now you can apply your KVL. Okay, when you apply your KVL, you will have, okay, can someone tell me what's the KVL when you have minus 20? Again?
Plus 430K IB.
Okay, great. Okay, 430K IB. Okay, and then
Plus VBE.
plus VBE, correct. Okay.
Plus IE,
Mhm.
110.
E1K. Yes, that's it.
But
That's all you have. Yes, thank you very much. Wen Chuan. Okay, so now you have two value. You have IB and also IE. Okay, you always want to make it with the only one variable only. Okay, change it to the IB. So you know that this one actually IE is equal to beta plus 1 IB. Okay, when you rearrange the equation, you actually will get something like this. So negative 20, okay, 430K
Hello,
IB. Hello?
the screen blur. Like,
Blur?
yeah,
Is it?
for me lah, I don't know.
Oh, how about the rest? Are you seeing blur screen?
No.
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 Yeah, I try the start lah.
Sorry, Noah, maybe you can
Check your internet connection.
left first and then come again. Okay, so this is 0.7 plus IB beta plus 1, 1K equal to 0. Therefore, IB is equal to 20 minus 0.7 over 430K plus beta. How much is beta? Beta is 50.
50.
Okay, 50. Okay, 50 plus 1, 1K. All right, so I need all of you to calculate this for me. How much did you get?
40.12 microampere.
Great, thank you. 40.12 microampere. So all of you get the same answer? Hello?
Yes, yes.
Okay. Okay, so look at the question. Now you have IB. Okay, now how to find IC? IC is equal to IC is equal to beta IB. Okay, once you get IB, okay, you have to times with beta. Okay, beta IB, which is 50 times 40.12 micro. So how much here?
2.006 milliampere.
All right, great. 2.01. Okay, that's it. Okay, for the IB and IC, at least you have done for the input loop. Okay, for the input loop. Okay, let's take a look on the output loop. Okay, output loop. All right, so I will add another slide here. Okay, so next part is to find the VCE and also VC and the rest. So this part is actually from the output loop. So output loop is from collector to emitter. Okay, from here means that from this circuit collector, okay, from collector node to ground to the emitter. Okay. So let's draw the circuit. Okay, you actually can combine it this way. Okay, this side. Okay, you can combine the circuit. But then I separated it. Okay, but actually if you want to save your space, okay, you can combine to the other side. Okay. All right, so let's take a look here. So for example, I want to combine. I just want to show you that you can combine. Okay. So this is your input loop. So we have done this part. Okay, so you have this 430K. Oh my God. Okay. Okay, and then you have 20 volt, and then you have resistor 1K. Okay, you have ground. Okay, so this is your base and ammeter. Okay, so still we are at second part. Okay, solve the output loop. Okay, from collector to ammeter. Okay. So from collector, okay, you have, this is your collector. Okay, what do you have here? So from collector, you have resistor 2K. Okay, you have resistor 2K. Okay, and then resistor 2K connected to plus 20 volt. Okay, plus 20 volt here. Okay, then you have plus 20 volt. Okay, and then the negative, where does it goes the negative? It will go to the ground. Okay, again, the same type one, you have ammeter 1K. Okay, ammeter 1K, so it will goes to here. Okay, as you can see, I can separate these two. So this is your input loop. This is your output loop. Okay, you can always combine the drawing. Doesn't matter, but you solve one by one. Okay, so you know that you have here, don't forget to write all the notation. You have VCE. From here to here, you have VBE. Okay, you have current here, IC. Okay, you have current here, IE. Okay, and then you apply your loop. Okay, I want to use to see different color. So this is your loop. Okay, your current loop. Okay, so let's like let us write the KVL. So KVL at output loop will be negative 20, and then hello. Hello?
Plus 2K IC
Yes, plus 2K IC. All right.
plus VCE
Plus VCE.
and plus 1K IE equals to 0.
Yes. Yes, 1K IE equals to 0. Thank you, Kawai. All right. Okay, so here it is. Okay, so for now, okay, we see that you can use either way. You can use IC equal to IE, or you want to use the value that you have calculated in IC, and then you calculate again IE, and then either way can. Okay, either way can. Because of what? Because IB is very, very small. It won't change much, the value. Okay, but now I want to take IC equal to IE. Okay, for this case, I want to take IC equal to IE. Okay, what is your objective? Your objective is to find VCE and VC. All right, so let's write down the equation. So you will get VCE is equal to 20 minus IC 2K plus 1K. All right, in here, you're going to have 20 minus IC. You have calculated the value, which is 2.01 milli. Okay, 2K, which is 3K. Can someone calculate from me? How much is VCE?
13.97.
Once again,
13.1.97.
13.97 volt. Okay, great. Okay, so next is VC. Okay, VC. Okay, if you want to do simplest way, where you already know VCE, you know that VCE is equal to VC minus VE. There you go. Doesn't matter. If you want to look at the circuit, you want to find VC. Okay, you know that VC from here. Okay, so your VC is here to the ground. Okay, what are you seeing here? So it is actually VC. You see what are the total voltage from this node to the ground? You can see VCE and also you can see VE. So that is the total voltage there. Okay, so here VCE you already have the value 13.97. How about VE? So VE is equal to what? What is VE?
1K time IE.
Yes, correct. So VE is actually 1K times IE. Okay, so 1K times, you can use IC value because IE equal to IC. Okay. All right. So this is 2.01 milli is about 2.01 volts. Okay. 2.01 volt. Okay, therefore here you will get 2.01 volts. So VC is about 15.98. Am I right? All right, right? Okay, okay. So now VE, you have the value. How you calculate VB? Okay, so VB is from this node, okay, where you see VB until ground. What are you seeing here? It is actually equals to total voltage at VBE plus VE. Okay, so 0.7 plus 2.01, so you will get about 2.71 volt. Okay, next, VBC. How you calculate VBC? VBC is equal to VB minus VC. Can someone calculate for me? VB minus VC? Hello?
Negative 13.27.
Negative 13.27
27.
volt. All right, that's it. Okay, so in BJT, there is quite a lengthy, I might say lengthy solution lah. So you have to do the input part and then you have to do the output part. There you go, a lot of calculation involved, okay, in BJT, okay. Not as much as in diode lah. I think in BJT involve a lot of calculation, okay. So make sure you understand from the input loop itself, okay, because that is your main, okay, where you get your IB, okay. If your IB is wrong, all your calculation are wrong. Okay, make sure your IB is very, very small, usually in microampere. Okay, you can see the importance of input loop. Okay, so you have to solve the input loop correctly, get IB correctly, and then you will get correct IC, and it will be applied to your output loop as well. Okay, so all are related. Okay, so it started from the input loop itself. Okay, IB must be correct and so on. Okay, quite a lot of calculation here. Okay, so you might need practice. Okay, do practice in order to calculate faster lah, faster. Okay. So you have done all this, okay, IB, IC, VCE, VE, VB, VBC, okay. So do you have any question before I move forward? Dear student?
No.
No, very clear?
Yes.
Very good. All right, okay. That's it. So this is the solution now. So you might not, so the solution is quite just equation there. I don't like you to follow this solution. Okay, I like you to understand this and this. Okay, where you can derive the equivalent circuit from the question. Okay, so make sure you know how to simplify the circuit and then write the KVL from the equivalent circuit. Okay, don't memorize this. There are some students who like to memorize, but I think there are a lot of things you need to memorize, not only these subjects. Right? Don't memorize this. Okay, understand this and this. Okay. All right, so I leave this exercise 2 with you. So can I trust you that you're going to do this? So next class, I ask you the answer. Is that okay? Student, are you
Yeah.
there?
Okay.
Okay.
Okay. Start talking to myself. Okay. All right. So, all right. Okay. We take 5, okay, before we move forward to the final biasing circuit. Okay? Maybe while take 5 you can do, or take 5, just take 5 without thinking anything. Up to you. All right. If you have any question, do let me know, okay?
The question.
Yes.
It's
What?
The exercise 2.
Again?
The exercise
One
2
more.
picture. You
Hello?
said that.
Wen
Can you
Chuan,
hear
I
me?
didn't hear you.
No, I say that the exercise 2 because I seen your screen, so I want to try it. Then you
Oh, okay. Sure. Very good one. Good boy. Nah, have a try. Okay, so your take 5 is to try exercise 2. Good. Well, take 5, you don't have to use your brain, just listen to me. Okay, so during quiz tonight, 8:30 sharp, okay, you can see the question and the e-learning. Okay, so you download it. Okay, I will give the password of the quiz file in the Telegram group. Okay. Okay, so I will so actually by 8:20 you can already see the quiz on the e-learning. Okay, you can download the file. 8:20 also I will give the password. Okay, so you can, after you everyone can download and open the file with the password, so you may start lah about 30 minutes. Very easy. I think for part A, just fill in the blank, about 10 questions, fill in the blank, and then part B, calculation. That's all.
Can you repeat, Doctor, please?
Yeah.
Can you repeat, please?
Repeat about test. Sorry, about quiz.
Yes, please.
Okay, for quiz, I will upload the question on e-learning. For those section 5, you go to section 5 e-learning. For those section 6, you go to section 6 e-learning. Okay, so the quiz, so you can actually see the quiz on e-learning by 8:20 p.m. Malaysia time. Okay, and then you download the question. Okay, I will give the password of the question in the Telegram group. Okay, please beware in the Telegram group. I will forward the password there. Okay, so by 8:20, I already give the password. Okay, you can open the file, you can put the password, and you can see the question. Okay, you can straight away start actually. Okay, and then you do for 30 minutes. Okay, but make sure 9, 10 you stop, and I don't know if you want to stop, but you need to scan your answer and upload. Okay, I give you 10 minutes extra, okay, to scan and upload. So by 9:20 there will be cut off time. Okay, 9:20 cut off time for you to scan and upload your answer. All right,
Okay, doctor. Thank you.
welcome. Okay, easy one, you can do it before 30 minutes, I bet. Yes. Okay, just fill in the blank and also calculation. Okay, have we done with 5 minutes?
How many questions, doctor, in the quiz?
Yeah.
I said, how many questions there?
So, Mantar, for the part E, which is fill in the blank, just fill in the blank. Not like tutorial where you have to describe the essay, something like that. No, just fill in the blank, 10 question. Okay, 10 fill in the blank. And then part B, 1 question for calculation.
Okay, no, doctor. Thank you.
Welcome. All right. I think I have enough with 5 minutes, right? More than 5 minutes. Okay. So please try this exercise 2. In the next class, maybe I ask you the final answer. Okay. Or all of you have tried this exercise 2 while I talked just now? Wenchuan, did you get the answer?
Yeah.
Great. Okay. Can you share with me the answer?
I find that is 29.1 at microampere.
Okay.
Well done.
How about the rest? So everyone try? Did you get the same answer like Wenchuan?
Yes, same answer.
Great. Okay, Azmil said same answer. Okay, ICQ?
0.91 at milliampere.
Okay, all right. So VCEQ?
At 0.62 watt.
8.62 volt. So how about others? Did you get the same answer VCEQ? Same like Wenchuan? 8.62 volt? Might be in the chat. Did you all try? Okay, go on. VC, Wenchuan?
13 watt.
VB?
No yet.
Okay, it's okay. So next class we'll give see the final answer. Okay, all right. So let's take a look on the final type of biasing. Okay, this is more. I can say this is more complicated. Okay, complicated. Okay, how does it look like? Like this. See, so you have more resistor here. So not only RE you have. So the name is voltage divider. Okay, what is the hint here? Where you solve it using voltage divider rule. Okay, do you still remember voltage divider rule? Same like Thevenin rule. Okay, so quite complicated where you have R1, R2, RC, and RE. Okay, so this voltage divider biasing commonly, this is a very common design, okay, in amplifier circuit. Okay, it use 2 resistor R1 and R2 as a potential divider. As you can see, you can actually do the voltage biasing, voltage divider here, which is I'll show you in easier way. Okay, and for this voltage divider bias, it gives good Q point stability, means that the voltage divider bias has better stability compared to emitter stabilized bias, and of course compared to fixed bias. So fixed bias is the weak one, okay, less stable, okay, compared to emitter stabilized bias. But now you have voltage stabilized bias, it is much more stable than these two. All right, so this method of biasing of the transistor greatly reduces effect the varying beta, which is this type of circuit does not too depend on the beta value. Okay, so it is more steady and has the best stability. Okay, again and again I put this. Okay, in the end of this class, I think you should have memorized this all. Okay, all right. Okay, so we have two types, okay, to solve this circuit, okay. The only type that will be covered here, okay, which is exact analysis using Thevenin theorem. Okay, Thevenin theorem means you apply voltage divider rule at this side. Okay, at this side. Okay, it's okay. I will show you how. Okay. All right, so step to solve, okay, sama, same, okay. First step, you remove the capacitor, become open loop, and then this is the equivalent circuit, okay. Do not forget to put all the notation, okay. You have base, you have collector, you have emitter here. Do not forget all the current as well, okay. And then you have voltage here, VBE, okay, voltage here, VCE. All right. Okay, so for the second step, so there you go for the second step. Okay, let me show you how. Okay, so if you want to draw again the circuit, okay, so this is how it looks like. Okay, so we use, so this part, okay, you have to solve it using Thevenin. Okay, actually you are seeing this from here. Okay, Thevenin from here. So if you draw again, okay, let's look together here. Okay, if you draw again, so at the base here, please follow me one by one. Okay, so you have base there, base. Okay, at base here, you have what? So at base here, you have two resistors, one to the R1, okay, one to the R2. Okay, so let's draw the R2 first. So every time you have circuit, see at base here, okay, you have R1 and R2. Okay, R1 and R2. Okay, but R2, okay, R2 is connected to the ground. Okay, now R2 is to the ground. Okay, so where does another point of R2 go? It goes to R1. Okay, so R2 again goes to R1. Okay, where does R1 goes? Okay, another terminal of R1 will go to the plus VCC. Okay, plus VCC here. And where does the negative goes of the VCC? Of course, it will go to the ground. Okay, so that's how they simplify the part of R1 and R2 here. Okay, all right, from here, okay, from here, we solve, so this part, from this part onward, we solve it using Thevenin theorem. Thevenin theorem, basically, it is a voltage divider rule. Okay, VDR is voltage divider rule, same thing. Okay, so what you need to find is the V Thevenin, okay, and R Thevenin. All right, before I move forward, do you have any question with the simplification circuit of R1 and R2? No question. Okay. All right. So how do we find R1 and R2? Okay, of course, from here to find R Thevenin, I think all of you know. Okay, so to find R Thevenin, you short circuit the voltage. Therefore, R Thevenin is equal to R1 parallel with R2. Okay, and then V Thevenin, of course, the voltage across here from this node to the ground is R2. Therefore, V Thevenin is equal to, okay, so R Thevenin from here. Okay, so R Thevenin here, you will get R Thevenin is equal to R1 parallel with R2. All right, so V Thevenin, of course, V Thevenin is from this node, okay, to the ground, okay, which is equal to R2 over R1 plus R2 times VCC. Okay, so that's how you find the R Thevenin and V Thevenin. Okay, do you have any question before I move forward regarding the Thevenin theorem part? Or all of you clear? Not yet, doctor. Okay, great. Okay, so this is your base part just now, so your base part. So you can expect that you have your BJT here. Okay, so the front part there will be your beginning of your BJT. Okay, so after you solve the Thevenin part of this R1 and R2, okay, using Thevenin theorem, where you got your V Thevenin and R Thevenin, okay, therefore your simplified circuit at the base to ammeter, okay, will go like this. Okay, so now at your base here, okay, will be replaced with your R Thevenin, okay, and the voltage here will be at the base here will be replaced with the V Thevenin. Okay, so this is V Thevenin, okay, and R Thevenin. So that's how you simplify the input part of your circuit, okay, where you have R Thevenin. Now everything, it is no more complicated as this, okay. So R1 and R2 has been transformed using Thevenin. So R1 and R2 here, there are no more R1 and R2, but now everything replaced with Thevenin, okay, at the base to ammeter. Are you all clear with this? All right, so for the output part, okay, since that you have solved the input part, okay, this part you have solved just now using Thevenin, R1 and R2. For the output part, okay, at the collector to ammeter here are the same as what you have solved in the ammeter stabilized circuit just now. Same thing. So if you want to draw at the input part, so this is your collector, therefore you're gonna have your RC here. Okay, and then you're gonna have from RC you have what? Okay, so you have from collector you have RC, and then you have VCC. Okay, at ammeter you have RE to the ground. Okay, so same thing what you have done before. Okay, so you have here VCC, and then this one to the ground. So this is your input loop. So this is your output loop. Okay, so which means that you can solve your IV KVL at input loop, now KVL at output loop. Do not forget you have here VCE. So current flow through here is IC. Okay, current at the bottom there is IE. Okay, and you have here IB. Okay, IB and IE. All right, so all of you clear or not on this part before we move to example?
Yes, madam.
Very much clear?
Yeah.
Great. Okay. Okay, great. Okay. Okay, so this is the same thing like I have explained just now, okay, but then in a proper drawing, okay, I hope you all understand. So the input loop and output loop has become the Thevenin part, okay, so you have Thevenin part here, V Thevenin, R Thevenin, so they draw it like this. So I think if you draw R Thevenin here will be understandable, okay, and then this is your input loop, okay, this is input loop. Okay. And this is your input loop. Okay, same thing. Okay, same derivation. Okay, don't have to memorize. Okay, so let's do the input loop here. Okay, so let's take a look here. So you have, for example, if I draw again like this, okay, I always want to draw again. Okay, so this is your R Thevenin, and then this is your V Thevenin. Okay, and then you have here your RE. Okay, this is your RE, this is your ground. Okay, so this is VBE. Okay, this is IB and IE. So this is your loop. Okay, so if you apply KVL here, okay, let's do together. So you have negative V Thevenin. What else?
IB R Thevenin
Yes, IB R Thevenin. All right, what else?
plus VBE
Plus VB.
Plus, yes, plus VBE plus,
IE RE.
yes, IE equal to 0. Okay, so IB and IE, you can change it to IB. Okay, beta plus 1. See, it is the same thing, right? Sama tak? It's the same thing, okay? VTH minus VBE over RTH plus beta plus 1 RE. Okay, so that's how you do it. Okay, same thing here, sama. The same thing. Okay, so the derivation is actually after you derive it, after you simplify the circuit, then you will be able to get the input loop and also the output loop. Okay, so that is the input loop done. Okay, for the output loop, okay, if I draw again here, so this is your output loop. So you have here base, and then this is collector. This is emitter. All right. So at collector, you have RC. Okay. And then at RC, you have VCC, not V Thevenin anymore. Okay. You have VCC because at output loop, nothing to do with the Thevenin. Okay. Output loop, same output loop like previous emitter stabilized. So you have RE here. Okay. And then you have ground. Okay, so in here you have IC, here you have IE, and plus minus VCE. Okay, quite long, but then practice makes perfect, right? So apply KVL, so you will get your KVL here. If I draw the KVL here would be negative VCC plus IC RC plus VCE plus IE RE equal to 0. Okay, so in here you will get VCE equal to VCC minus IC RC plus RE. Why? Because IC is approximately equal to IE. Right, the same thing. Yes, the same thing. You don't have to worry about it. Okay. All right, so let's take a look on the example. Okay, I think this example we'll do it together. Okay, we'll do it together so that you can do the exercise on your own. Okay. Okay, so just like that, determine VCE and IC. Okay, looks like VCE and IC is at output loop. Okay, but then, oh, I don't have to solve for the input loop because they just want IC and VCE. No, you have to solve from the beginning of the story, which is the input loop. Why? Because you want to get your IB. Okay, IB. Okay, let's do together part by part, all right? Okay, so you have your circuit here. Okay, so let's solve this part first. Okay, the R1 and R2 part. Okay, this part we want to solve it using Thevenin. Okay, but first thing first, what is it? Open circuit the capacitor. Okay, when I put like this means open circuit capacitor. Okay, okay. First step is open circuit capacitor. Okay, all right. Second step is to solve your solve Thevenin part. All right, let's us look together. Okay, so you have base here. Okay, so let's redraw again the base. So you have this is your base. Okay, base. Okay, okay. At base you have this resistor to the ground. Okay, take this resistor first to the ground, which is 3.9K. Okay, and then this 3.9K have another connection. Okay, here with another resistor, which is 39K. Okay, where does this 39K goes? Okay, 39K goes to plus 22 volt. Okay, plus 22 volt. So the negative part will go to the ground. Okay, so now you are solving the V Thevenin. Okay, sorry, I use VTH. Okay, VTH here. So V Thevenin at this, you are seeing from here. Okay, Thevenin from here. Okay, now let's together calculate the what is V Thevenin, students? Student?
3.9K
3.9K.
over 3.9K plus
Right.
3.9K
All right.
times 20.2 volt.
All right. Thank you, Azmil. So what is the value for V Thevenin?
What?
One more time.
2
2
Two.
volt. 2. All right. 2 volt. Thank you, Wenchuan. All right. So 2 volt. All right. So now R Thevenin. Okay, R Thevenin equals to what? Banyak dah I membebel tadi, right? R Thevenin.
3.9K parallel
R2.
with
All right.
39K.
All right. 3.9K parallel with 39K equals to
3.55K.
Yeah, same.
same. Great. Okay. So you have both, okay, the V Thevenin and R Thevenin. Now you want to draw your equivalent circuit. Okay, I need to have another slide to draw the equivalent circuit. Okay. So I need to copy this. Okay. Give me 1 minute. Not 1 minute, 2 seconds. Okay, so now let's draw the input part and output part, right? So now this will become like this. So I want to draw my circuit like this. So this is, okay, your base, okay, collector, emitter. Okay, so at base right now, okay, at base right now, there is no longer R1 and R2. Okay, there is no longer this resistor and this resistor. No, these two resistor has been simplified to R Thevenin and V Thevenin. Therefore, at the base here, okay, base here you have R Thevenin. Okay, R Thevenin. Okay, and also V Thevenin. Okay, no longer 22 volt at the input. Okay, now you have V Thevenin. Okay, so this is V Thevenin. Okay, all right. So the ground part, the negative will go to the ground part. Okay, don't forget you have emitter. So at emitter, so base now settle. At emitter, you have, of course, you have resistor. RE 1.5K, okay, and then you have ground like this. So this is going to be your input load, Okay, don't forget you have here IB and here is IE. Okay, put all the notations so that in your voltage, in your KVL, you won't forget everything here. Okay, so R Thevenin is 3.55K ohm and V Thevenin is 2 volt. Okay, now KVL at input load. What is the KVL at input load? Let's start with -2. So what are the input load KVL? Student?
V2
Plus
plus
IB, RTH, okay, plus
VBE,
VBE plus
IE.
RE. So can I straight away write IB beta plus 1 RE?
Yes.
Yes.
Right. Okay. So don't get bored because I also have to write it many times. I hope you in there. Okay. So IB is equal to 2 minus VBE is 0.7 over RTH is 3.55K plus beta is how much? 140 plus 1 and RE is 1.5K. Can someone calculate IB for me?
Six point zero five microampere.
6 point. Oh, I don't have the answer. Too bad. Okay. Again, one more time. Nanchan?
6.05 microampere. Well, I calculate again.
Okay. Maybe all of you calculate first too.
Yeah, same answer.
Same
6.05.
answer. 6.05. All right. So can you find IC?
Can.
Beta IB, which is equals to
140.
100.
F.47 10 power -4.
0.8, can I say?
10.
Zero.
0.5 milliampere.
0. How much? Again, one more time. 0.8.
0.47 milliampere.
Oh, 47 milliampere. Did anyone get the same answer like Wen Chuan?
same answer.
Same answer, Vidya.
Great. Okay, so now let's start for the output loop. Okay, output loop. Okay, output loop you have here collector. Okay, now these are all open circuit, the capacitor. So for collector, you have resistor 10K there. Okay, 10K and then 10K connected to 22 volt. Okay, this is not V Thevenin, this is 22 volt. V Thevenin doesn't do anything to do with the output loop. Okay, and then this negative will go to the ground. Okay, there you go. Okay, so your output loop will be, so you have here IC, okay, and at the bottom part you have IE. Okay, so this is your KVL. Don't forget to put notation for VCE. All right, so KVL at output loop, okay, will be -22, okay, plus IC 10K plus VCE plus IE RE equal to 0. Okay, so IE and IC, I want to make it the same. Okay. Okay, therefore VCE is equal to 22 minus IC 10K, sorry, 10K plus 1.5K. So this is RC plus RE. So 22 minus IC 0.8. Oh, sorry, 0.847 milli. RC is 10K plus 1.5K. So can someone calculate for me?
12.27 volt.
One more time.
12
Azman?
point 12.27 volt.
12.27
27 volt.
volt. 27 volt. Okay, did anyone get the same answer like Azmil?
Yes, same.
All right, great. Okay, so we have done both. Okay, so the question just one IC and VCE. Okay, you have done that. Okay, so simplify the input loop here using Thevenin. Okay, and then you can draw, I think you can draw straight away like this. You combine between input loop and output loop. Okay, so this is your output. Okay, and this is your input. All right, so that's how you do it. So do you have any question regarding this? Oh, very
No
clear.
question.
Very clear. Great. Okay. So quite a lengthy solution here. So I have put everything one by one, but then the same thing lah. You can always refer to what I have summarized here. Okay. So very long. So you can look at the solution here later. Okay. All right. Okay. Okay, so for this part, okay, I want everybody, why the other part I ask you to try on your own. Okay, this part I want you to try now. Okay, because of what? I think in terms of final exam, they couldn't have much more complicated than voltage divider rule. So most of the question will actually involve with voltage divider rule. So let's try. I mean, I want all of you try now. Okay, at least find the IBQ first. Can you all do it now?
Okay.
Okay.
All right. I'll wait for you 5 minutes to find the Thevenin first, maybe.
IIT.
All right, great. Sorry. Maybe I share like this. This way. Can you see what I'm sharing now?
Yes, doctor.
Yes, doctor.
Great. Okay. All right. So that both of us can see. Okay. So for the Thevenin, for the Thevenin, okay. So you solve this part, okay. From here to here. Hey, why this color? Oh. 100. Okay. So you resolve this to here. Okay, the Thevenin. So you are actually have, this is your, okay, so this is 9.1K, okay. Okay, that 9.1K, and then you have 62K, and then you have this is 16 volt. Okay, so you solve the Thevenin. Okay, our Thevenin is 9.1K parallel with 62K. How much is this, student?
7.94K.
And one more time.
7.94 kilo ohm.
All right. Does anyone get different answer or same answer?
I got same.
Great.
Same answer.
Same answer. Great. Okay. So V Thevenin is equal to 9.1K over 62K plus 9.1K times 16. How much here?
2.1 volt.
2.1 volt. And everyone get 2.1 volt?
Yeah.
Great. Very good. Very good.
If
Okay.
I get 2.04x,
2.048.
4x, because I take
I'm same with Wen Chuang.
Oh.
Yeah, I got 2.05, but also same, we can make it to 2.1, right?
Can guys, boleh. So yeah, I calculate like 2.05 milli. How many ni? Okay, 2.05 volt, right?
Yes, madam.
Yes.
All right. Anyways can. Okay, doesn't matter. Either way is correct. Okay, 2.1 volt or 2.05.
Madam, even though it's 2.047x, then I
The
can
actual one 2.0.
47x something.
I see.
Can be
Then,
can 2.1.
then better take 2.05 volt.
5.
Okay, 2.05 volt. Okay, better take this one. Okay, all right. So for the input loop, okay, so let's solve for the input loop. Let me show you here. So for the input loop, okay, another slide. Okay, so for the input loop, you have this circuit base, and then you have R Thevenin, okay, and then you have V Thevenin, okay. At ammeter, you have resistor, how much? 0.68K. Okay, R Thevenin just now is 7.94K. Okay, V Thevenin is 2.05 volt. Okay, like this to the ground. Okay, so you don't forget to put the notation VBE. All right, and then you have here IB. So this is your KVL loop. KVL at input loop. All right, so you have negative 2.05 plus 7.9 for K IB plus 0.7 plus beta plus 1 IB, RE is 0.6 K ohm equal to 0. Wow, what a long equation. Okay, how much here? IB?
21.4 microampere.
Right. Wow, Wen Chuan has right all answer there. So let's refer to the answer here. IB is equal to
IB is 21.4 microampere.
21.
0.4. But because I take more significant, maybe we got some different.
Yeah. How about the rest? Did you get 21.4 microampere?
Yes.
Yes, okay. And then IC is equal to beta IB. How much the value?
1.712 milliampere.
All right.
712.
712. Okay. All right, great. Okay, so let's solve for the output loop. Okay, so output loop. So you have collector here, and then you have your resistor, RC. Okay, at RC you have VCC to the ground. Okay, your VCC just now is 16K, RC 3.9K. Okay, 3.9K and 16 volt. Okay, so you have IC here, and this is IE. Now apply KVL. So I will write my KVL here. KVL at output loop will be minus 16 plus IC 3.9K, okay, plus VCE, okay, plus IE times 0.68K equal to 0. Okay, so from here you will get your VCE equal to 16 minus 1.712 milli times 3.9K plus 0.68K. How much VCE? Let's refer to Wen Chuan answer is 8.16 volts. Are those correct? Anyone?
Yes.
Yeah, the
Same.
Great. Okay, so we have done this, and this. Okay, the rest here you can find on your own. Okay, so VC, VE, and VE, and also VB. So I will give you the solution. Okay, so this is the final answer for the VC. Okay, and also for the VE, and also for the VB. All right. Okay, so I think that's it for today. Okay, do you have any question regarding voltage divider rules? I will upload the updated slide as of today after class. Okay.
okay.
All right. Do you have any question? We finish.